All right, Calc 30, 5.1, we're talking about curve sketching. We've already talked about x-intercepts and about symmetry. All right, we're going to talk about vertical asymptotes here today in 5.1. So if you have a rational function, this is where you're going to see vertical asymptotes most of the time, is when you have some kind of rational function. So you have a polynomial in the numerator and a polynomial in the denominator. So this is going to yield you perhaps a vertical asymptote. A polynomial is, you're not going to have a vertical asymptote. You may have, just a polynomial function, like if it was just, y equals x squared plus 2x plus 1, just a polynomial function, there's no vertical asymptotes there. But it's when you start dividing by a polynomial that you might have an asymptote. Okay, so how do we start to deal with or find out if we have asymptotes? Well, if you have something like this, you have to look to see where the denominator might equal 0. Okay, that is a huge thing that you want to look for right away. So is there a value for the variable that would cause the denominator to equal 0? All right, so over here you're looking at x squared minus 1. This is the denominator. And you want to find out, hey, what value could cause a 0? Well, 1 could. 1 squared minus 1 is 0. But also negative 1. Negative 1 squared is positive 1 minus 1 is 0. So what you want to do is you want to factor the denominator to be sure that you've got all the possibilities exposed. So factor, if the you want to factor the denominator. Okay, so let's do that first, then I'll get into what the rest of this point says. So y equals, this is going to look like y equals x plus 1 over x plus 1 and times x minus 1. Okay. So the restrictions in the denominator look like x equals plus 1 or minus 1. Now, just because we have values for the variable that are restricted does not mean that we have a vertical asymptote. Okay, maybe you've forgotten from PC30 what a vertical asymptote looks like. Let's just back up a little bit. So if we have a graph that kind of looks like this and it kind of goes up like this towards infinity, and there's some kind of x value here that is undefined in this graph, and then you might see something like this where the graph kind of comes up like this. So this dotted line, this vertical dotted line, would be called an asymptote. All right, and it's an undefined region. We also notice that there's usually something extreme that happens just on either side of this dotted line, where the graph usually races towards infinity or negative infinity. So that's something else we'll keep in mind. But the key to finding out this point right here, whatever this is restricted values. So a restricted value is going to give us a clue as to what this is. Not every restricted value will give us a vertical asymptote, though, and that's where we're going. So possible asymptotes, or at least restrictions, x cannot equal 1 and negative 1. Okay, we know that. All right, so here's a question you want to ask yourself. You want to make this part of your notes. So if we have a factor in the denominator that can be divided out. Okay, so we look at this. Once we've factored everything, I see that I have this factor of x plus 1 that can be divided out of this ratio, right? So that would be a factor in the denominator that can be divided out. At that value, at this restricted value of this factor, and that's the negative 1, right, restriction that's attached to this factor, that means that at this x value, we have something called a gap discontinuity. A gap discontinuity. So you're writing these down in your notes here, okay? If factors can be divided out of a rational function like this, then that restricted value represents a gap discontinuity. And I'll finish this second point before I explain why that is. So B says that if the factor in the denominator, if a factor, okay, so like this one is the x minus 1 we're talking about here. So if this factor is in the denominator and it cannot be factored out, that is when in the simplified version of this rational expression, whatever factor is left in the denominator, that is usually the vertical asymptote. So the one that remains in the denominator when this is all simplified. So I'll just pause there and I'll talk about 1a and b some more. So we do have restricted values, x equals 1, x equals -1. We know the function is undefined at those points. What is happening at those points depends upon the simplified version. So when this is simplified, the x plus 1 factor is gone, and I have this left over. All right? So this is the simplified version right here, the simplified version of our rational function that we started with. The factor that gets factored out, that's the x plus 1. Right here, the x equals -1 is the restricted value. There is a gap discontinuity, a gap discontinuity at x equals -1. And what we're going to find here when we graph this and do some more examination is that we are going to have a vertical asymptote at x equals +1. That would be the restricted value for the factor that's still in the rational, simplified rational expression. So we're going to graph this, and I'll show you what this looks like, but I guess quickly point 2, there may be other restricted values like a negative under a square root sign and things like that. You have to be careful with those two. Those may represent gaps or vertical asymptotes, but they'll take some further examination. So the two basic things you want to pull out of this is if you have a factor that has an x in it that can be divided out, it is not a vertical asymptote, but it's just a gap. If you have a factor that cannot be factored out, then that's a vertical asymptote, almost always, and for I think pretty much all of the examples you're going to deal with. Question? Yeah. You can have multiple vertical asymptotes, you bet. Yes, absolutely. All right, so the graph of y equals x plus 1 over x squared minus 1 looks like this right here. Okay, this is the graph that we're dealing with here. So I'm just going to snip that into our notes here. And why is this important? Well, you're going to see a couple things. First of all, you're going to see that we certainly do have what appears to be a vertical asymptote right in between the two arms of this graph right about here, which is x equals 1. So a vertical asymptote at x equals 1 appears to be confirmed by our graph. All right, so x equals 1, if we drew a dotted line up and a dotted line down, you'd see that that works out pretty good. Okay? Now, what about x equals -1? Because at x equals -1 over here, it looks like I've just got a regular solid graph. Now, what our math is telling us is that should be a gap discontinuity. So let's go back to Desmos here, and let's zoom in. Okay, let's zoom in. And right about here still looks pretty solid. I'm going to zoom in like, hundredths, thousandths of a unit, 10 thousandths of a unit here. I'm zooming in. I'm getting into big time territory here. I think I might have wandered away a little bit. That's as far as I can zoom. Okay, so I was looking over at the scale there. Let's zoom back out, see if we can find -1 again. I have to be careful here. Okay, so we didn't see anything, but here we go. Oh, it's over here. Okay, let's try and keep our eye on that line. Okay, I'm going to be focused here, right here. That's where the point is, right there. So obviously it looks pretty solid here, but when we zoom in, let's see how far we can get. This is -1.0001. Okay, this is not working. Where is my gap? Let's go back to home. Okay. Can we? Oh, there we go. Look at it. Okay, usually that gives us a pretty, it actually shows the gap if we zoom in. I'm not sure why. I guess it stopped before we got there. But if you notice this, -1, x equals -1, the function is undefined because this factor is going to be divided out in its simplified form. This graph is a graph of the simplified form. Okay, so if I just did this with a different color and I did y equals, and what were we left with? 1 divided by, okay, so this is what, x minus 1, right? X minus 1. Look at that. So that's the same graph. Except on the blue graph, if we go to x equals -1, look at that. -1. So there is a point there on the simplified graph, but because the original graph was not the simplified graph, it's this red graph instead, then there is an x value that is undefined, and right there. Okay? So we have to be careful there. And it's in the process of simplifying where we note restrictions and see what happens in the simplified version. That's where we can determine what kind of gaps or discontinuities we have. Because there's a gap discontinuity where the line appears solid, appears to be a continuous function, but boom, at one point, there's a little space that's open. And then an asymptote would be a discontinuity, and again, that means it's discontinuous, where the graph seems to race towards infinity on either side of the asymptote. And sometimes the graphs will be such that the graphs will race towards infinity in the same direction. You could actually have graphs like this, where we got race towards infinity, and coming from the other way, races towards positive infinity as well. So this happens as well. You'll see that too. Okay, was there a question there? Okay, so good question. Let's go back to Desmos. If you look over here, the simplified version, this is just a function all on its own, this blue one now. It doesn't know about any other restricted value. So this is just 1 over x minus 1. And yes, it's continuous here. It's continuous. But when we have this original one where we do have another factor involved, we have minus 1 that is now has a restriction. Where did I think? Oh, just so hard to get to right there. Okay?
Would 1 be a restriction?
1 is not a restriction for, so if we go back here, for this one, 1 is not a restriction, or -1, sorry, is not a restriction here. 1 certainly is, because it's still here. But -1 for this graph is not a restriction. That's 1 over -2. That's fine. That's -1/2. And that's what we see in our graph. Okay? All right. Okay. Now what we're going to do is we're going to use sign analysis to find vertical asymptotes. So you remember sign analysis? Write this example down here, and let's use sign analysis and see what happens when we examine this. So just take a moment to just jot that down. All right, so let's take a look at this. Now, in order for us to find out if there's any vertical asymptotes, remember the keys will be to examine the denominator. And we do have to factor this if we can. So we want to see what the factors are. We have to know what x values would make this 0. And so I'm going to factor the bottom and write this like this. Okay. Two numbers that multiply -6 add to -1. Looks like we got -3 and +2. Okay. So that's this trinomial factored. All right. So what we have here is we have two restrictions. So x, x, the restricted values would be +3 and -2. Okay. And we're going to use sign analysis now to see what happens at +3 and -2. What happens? So sign analysis on this function, not on the derivative. We're not talking about that. We're talking about just the function. I'm going to put all the factors, x, the x minus 3, and the x plus 2. I'm going to put them all in here. So x, x minus 3, x plus 2. And I'm going to find out what the function, or y, or f of x, actually looks like here. Okay? Now what I do is when we're examining a function where there's division, I usually put a little dotted line here to remind myself that we're taking x and we're dividing it by x minus 3 and dividing it by x plus 2. So that might help. Because multiplying by 0 is different than dividing by 0, right? So what does this look like? When is x equal to 0? Well, x is 0 at 0. X is negative when x is negative. X is positive when x is positive. So yeah, we're going to do all the factors in this to determine, what's happening, okay? All right, what about x minus 3? Well, that's going to be at 0 at x equals +3. Nice. It's going to be, it's going to be negative before that. Uh-oh, what does that mean? Bad news. This means bad news. What that means. Oh, crashing. Okay. Going click here or press enter. Okay, hang on. So we have negatives here, right? And we have positives over here. So again, if you're unsure about this, just pick a value like greater than 3, like 10. 10 minus 3 is positive 7, so you know it's positive over here where 10 would be, and it's negative at 0. 0 minus 3 is a negative value, so it's negative over here. And then do the same thing for plus 2. That's going to be at negative 2 is going to be where this is 0. Negative and positive. Okay, so the function is, watch this, the function is going to be a negative divided by a negative times a negative, or a negative divided by a positive, that's going to be negative here. Okay? Now, this is, I don't know if I should draw this, but I'm going to draw this little line. That's not going to help maybe, but this is a negative divided by 0. A negative divided by 0. That is undefined. So we put a little infinity sign there because we're dividing by 0. Okay? Here we have, in this next region between these two numbers, we have a negative divided by a negative. That's going to be positive. We have a 0 divided by something, so that's 0. If you have a 0 on top, that's okay. When you have a positive divided by a negative, we've got negative. A positive divided by 0, it's going to be undefined again. And then a positive divided by a positive. So what does this tell us about the function? Well, it tells us where the function itself is positive and where it's negative. And positive means it's above the x-axis, and negative means it's below the x-axis. Okay, so that's what I can tell here. As I try and make some space. Okay, so if I were to graph this, okay, just a quick graph here, all right, then the function will be negative, below 0, going to negative 2. Okay, so negative 2 is here. The function's going to be down here somewhere, and then it's going to go to infinity. It's going to be infinity at negative 2, so it's probably going to race down towards, is that going to be a negative infinity or a positive infinity? Well, if it's negative here, it's not going to cross into the positive region to get to positive infinity. So it's going to stay down to negative infinity. You see? That's this part right here. On the right side, it's going to be positive. So it can't be down here. It has to be up here. Okay? So it's probably going to be coming down somewhere. This is 0 here. So guess what? It looks like it's going to come through 0. Right? Y is 0. The function value is 0. And then it's going to go into its negative. And it's going to hit negative, and it's going to hit infinity at 3. And then it's going to be positive, so it's looking like this. Okay, we don't know exactly what's happening there, but this is a rough sketch of what this sign analysis is telling us. And let's focus in on this right here, guys. Okay, when you have the function being negative, and then it's undefined, and then it's immediately turning to positive, that's an asymptote. That is an asymptote right here at x equals negative 2. So this is asymptote. Negative, infinity, positive. That's an asymptote. Over here as well, this grouping is an asymptote as well. Negative, infinity, positive. So that is an asymptote as well. Negative, infinity, positive, asymptote. So to answer your question from earlier, yeah, you can have, was that your question? You could have more than one asymptote. Not sure who asked that over here, but okay. So we don't know exactly what values f of x has, but we can see through sign analysis where our asymptotes go. Okay, and our look at the function. Let's relate this now to the graph because it's important. X equals positive 3, right? That's an undefined term, and this in the simplified version is still in the simplified version here. So guess what? That's an asymptote. Yes. This one over here, x plus 2. So that is x cannot equal negative 2. This factor is still in the denominator in the simplified version, so it's an asymptote. That's true. So do you see how an examination of the function and the graph matches up here? Yes? Question? So yeah, so you're asking about this infinity sign here. We have a negative value, negative, divided by a negative value times 0. This 0 is this from this 0 right here, and it's in the denominator. So when you have a value divided by 0, that's undefined. We'll show that as infinity. Undefined, that's how we'll show that. Okay, so whenever you divide by a 0 here, we have a positive number dividing by 0 times a positive number. That's a number divided by 0. That's infinity. That's undefined. So we'll write it as infinity there. If you have 0, well, yeah, if you have two factors and one of them is 0, then that product is 0. Yep.
So we're dividing,
Okay.
dividing the signs?
Look at. This is on top. That's the numerator.
Yeah.
This is dividing. So we're dividing by this. That's why on the side I had this and then the dotted line here to show that we're dividing by these two factors. So in this case right here, we have a negative value on top. When x is in this region, we have a negative value on top. We are then dividing by a negative number times a negative number. So that's a negative divided by a positive. That's why the result is a negative, overall negative. Okay? Yeah. So before when we were doing sign analysis, they were just factors that we were multiplying. But now we're talking about rational equations. So in sign analysis, we may have to divide. Yeah. So that's why this is 0, because it's on top, the numerator. This is undefined because the 0 is in the denominator here and here. Is that making more sense now? All right, so now we're going to talk about using limits. Using limits. How do you use limits, you say, Mr. Maxwell? Well, you identify your restrictions, okay? So x equals 3 and x equals -2 are points of interest here, right? That we may have some kind of asymptote, okay? So if we use limits, I want to find out what happens in and around each of these numbers. So let's find out the limit right now, and we're going to use one-sided limits here. We need to find out what is the limit of this f of x, this function right here, as x approaches 3 from one side. Let's start with the left side. Okay? And this is going to be important moving forward in calculus to think about limits here. And I'll show you how this is done. All right? So what happens, and we have the luxury of knowing what this graph looks like over here, right? So we know that the graph looks like it's going to tend towards negative infinity over. That's what it looks like, okay, from what we know already. So if you're given just this question right here, just this, because this will come in calculus here, you'll say, well, what's this limit from the left? Normally what we would do is we would plug 3 in and see if we could find out what that does. Well, 3 gives us an undefined value. Okay, that's not going to help. So from the left side, okay, this is positive 3 from the left. So this is what you do. Literally, this is what you do. You say, as x approaches 3 from the left, that's going to be something like 2.9999. Does that make sense? From the left, x itself is going to be 2.99999. So it's going to be pretty much 3. What's going to happen to this factor now as x approaches 3 from the left? So I've got about 2.9999. Let's just make a number that's really close and stick it in there. Okay? And this one, well, this is going to be like 2.9999 plus 2. So this is what you're thinking in your head. You're literally thinking of what's a number that's really close. Let's see if I can get some kind of sense as to what this function is behaving like, or what the value this function might be getting close to. And so you would envision this. So this is going to be around a positive 3, okay? So that's fine. You can say you're going to have a positive value, all right? And positive 3, if you want to write positive 3, that's fine. What about this one? So this is 2.9999 minus 3. This is going to be a very small negative number, right? That's what this factor is going to be. And as x approaches 3 from the left, this number is going to get smaller and smaller and smaller, like 0.000000001, right? But it's always going to be negative because this number is smaller than this one. And this one over here is just going to be a regular old positive number, okay? Okay? So this is what we can figure out, that we have a regular old size positive number divided by a regular old size positive number, but this whole denominator is going to be very small. The whole denominator is going to be small, and it's going to be negative. Okay? So that means we have a positive divided by a negative, and this is going to be super, super small, super, super small. When we divide a regular old number, like around 3, by a very small number like point, 0.00000000000000001, we get a very large negative, largely negative number. Okay? And again, I'm writing out for you what you're going to be, doing as you work through this, because you can't simplify into this. You can't get rid of any of these factors. So you have to envision what's happening. And of course, the important thing to focus on is what's happening near this value here, okay? Because this is the x value in question that's going to give us a bit of a problem. So a large negative value. So that means that in the graph, we have negative 1,000,000 right here, see? It's down here. Negative 100, negative 1,000, negative 1,000,000. It's approaching negative infinity. That's reasonable. What happens, okay, so now, what happens here, I'm going to just change this. What happens as the limit approaches 3 from the right? Because in order to use limits to examine vertical asymptotes, we have to let x approach the value from the left and from the right and see what's happening. And so that's going to be over here now. Let's do it over here. So I'm going to jump right to this stage right here. I have a positive number because it's still positive 3. What happens to this factor? Well, this is going to be a very small, because it's going to be close to 3, but it's going to be a very small positive. You see that? And this is just going to be a regular old positive number. So a positive divided by a small, very small positive means that we are going to have a very large positive number. So here you see on one side, as x approaches 3 from the left, okay, so the limit of f of x as x approaches 3 from the left, we have a large negative, and the limit of the function as x approaches 3 from the right, we have a very large positive. And so, of course, that does tell us that we have a large negative here and a large positive up there. So that's going to be our vertical asymptote. When you have very large and opposite sign, then you know that that's going to be a vertical asymptote, okay? Because, of course, we're undefined exactly at 3. So jot this question down too. This is part of your assignment. This would be one where we will have to run through. We can't factor this and divide out any common factors to make this real nice and easy. We can't just put 9 in because it's undefined. So we have to kind of work through in our brains what's happening here. So let's go from the right here is what it asks for. So we've got something like, here's 9 over here. And what's happening to the graph in this region right here? Does it look like, because this is a restricted value, does it look like it's going largely positive, or does it look like it's going largely negative leading up to 9 from the right side? That's what we're examining. Okay, so let's take a look at that. And what you would do is exactly what I did here before. You would say, okay, so 5 minus something that's almost 9, or 5 minus 9.0001, okay? And this is going to be square root of 9.00001 minus 9. That's what you're thinking in your head. And again, just pick a number that's super close, but on the right side of 9, so just greater than 9. Okay, so this is going to be a negative number. Do you see that? 5 minus almost 9. That's going to be a negative almost 4, right? So that's going to be a negative number. This one here, okay, so inside here, I'm going to have the square root of a super small positive number. You see that? It's going to be super small, like 1 times 10 to the negative 1,000, right? Super duper small. And we're going to take the square root of that on top of it, so it's going to become even Well, it'll become a little bit bigger technically, but it's still going to be super small. Okay, so you've got a negative by a small positive. When you divide by a small number, you get a very large value. When you have a negative divided by a positive, okay, let's go over here. You have a negative large number. So the limit on the right side there of 9, here's 9, it should be going down to the negative region right here. And that's what you're asked to find. And of course, what you might want to do is graph this and find out for yourself looking at the graph. In this chapter, you won't have a graphing calculator to graph this stuff to figure out, but while you're learning, while you're putting the pieces together, you can certainly graph to check anything. Okay, so let's do that now. All right, so here we got our graph here, and here's 9 right here. And notice that as we go up from there, you see it's still 9. It's actually looking like there is an asymptote right here. You see? This is still 9 right here. So the graph is coming towards 9, but it's never going to actually touch 9. It's just going to get closer and closer. Okay? See that? And as x gets larger and larger negative, of course y is going to get larger and larger negative too. You see this? So it's getting close to 9 from the right, getting close to 9, and the number is just jumping down, and it's going to be super, super large, okay? I don't know if we can actually, but there you go. It doesn't quite hit 9. It might not be able to give me much of a value here. Yeah, it's not going to be able to talk to me here. Yeah, it won't. Too much thinking. Okay, so that's how you interpret that. Just look at positive, negative, and if something's small, something's large. And you may have a very small number on top, okay? A small number divided by a regular sized number is going to be a super small number, okay? What was the point of this? That's your question? What's the point of this? Make you smarter. So we're examining vertical asymptotes. Examining. So you're looking at a function like this. Okay, let's say I give you this function right here, and I asked you to find intercepts. I asked you to find asymptotes if there are any. Okay, and you go to factor this, and you're like, oh my goodness, I cannot really factor this 5 minus x. It seems to be factored. I can't really factor root x minus 9. It seems to be factored. So the whole factoring and dividing out common factors like we started this lesson with, that's not possible. So the point of this one is to use limits to see what happens when we can't factor. So I probably wasn't that clear on that earlier. I apologize. That's why we're doing this, because we can use limits to find out about vertical asymptotes as well. And they will come in very handy when we cannot factor the top and the bottom, or even if we can. If like this is factored and there's not much we can do about this, but we can't see if there's any factors that divide out. There's no factors that divide out. So we've got an issue at 9. So what happens at 9? Is it a gap? Is it a discontinuity? And what does the graph look like? So we use our limits to find out what it looks like. Okay? Yeah, so you can use sign analysis like we did here at the first. Okay, or you can use limits and just think through this logically to find out, hey, is this value going to be large or small? Is it going to be positive or negative if I approach from one side of that restricted value? Alrighty?
Okay, my question where we have to, right now we don't have numerical values.
Yeah, you can actually pump in actual numerical values here too. Sure, yeah. If you want to put in 9.01 and then 9.001 and then 9.000001 and see where those values tend towards, that's a great idea. But you usually only have to do it once. Even if you put this into your calculator, you could put this into your calculator and you would get a largely negative value. Yeah. So a lot of times you don't have to, because this is still a simple function actually, right? If you have like a big long polynomial or a big long crazy thing and you pump it into your calculator, yeah, you could. But you could, a lot of times you could just kind of work through it logically. So that's a good point. If you want to actually put this into your calculator, I would encourage you to do that right now and see what value you get. You're going to get a negative something, and it's probably going to be on the larger side. Okay? So you go ahead and do that right now. Maybe I'll do that here on this side too, and we'll compare our answers. Okay? Let's try that. So actual pumping this into the calculator, see what we get to. Did you get something that looks like that? Okay, so that's okay. So we might have used a slightly different decimal here, but yeah. So I get negative 1,264 or so. So that's a large negative number, right? So as this gets okay, so let's just back this up. Let's delete this. Let's see if I can put my entry in again, and instead let's go up here and let's insert a 0. So I'm going to insert a 0 here. Okay. And I'm going to go over here and I'm going to insert a 0 here. Insert a 0 there. And then I'm going to see what happens. Look at that. So you might have used that one. That's the one you used. Okay, that's the decimal you used. And these are getting larger and larger negative, right? Okay. Awesome. Okay, you can do your 5.1 assignment.